Why trees are useful. So decision trees need not be classifiers. They could be used in regression. They can also be used in unsupervised. But probably the most important thing about decision trees is that they are trees, graph theoretic trees. So decision trees in practice have a bad reputation and they deserve it. They tend to overfit the training data. They produce arbitrary, unstable, and even sometimes comical sequences of decisions. A decision tree used as a classifier can only classify data that is linearly separable, and it better be well separated. A decision tree used as a similarity kernel can only produce disconnected unions of complete graphs. So why do we use decision trees at all? Well, a decision tree is a tree, as in graph theory, networks, tree. A tree is a highly intuitive, easy to interpret, and easily applied network model of decision making. A tree is diagnostic. It not only makes predictions, but also provides the reasons or rules for its predictions. Machine learning algorithms are often accused of being black boxes because the process for making predictions is hidden. But a decision tree is completely transparent. Its predictions are a result of its decisions. Trees are also useful because they're intuitive. Probability often is more intuitive with a tree. The leaves are mutually exclusive events. If you have A as observations in one leaf and B as the set of observations in another leaf, their intersection is the empty set. So therefore, the probability of multiple leaves is the sum of the individual leaf probabilities. Because if the intersection is the empty set, the probability of their union is the sum of the probabilities. Suppose, for example, we have x associated with 1, 2, 3, 4, 5, and with probability distribution p of x. Our first decision x less than 3 is in this illustration leading to a decision x less than 2 and 3, 4, 5. That's a leaf, an outcome of a sequence of decisions. And we're going to label edges with the probability that that edge occurs. Now we have a possibility of x is 1 or x is 2, and we label with the probabilities. The sum of the probabilities is the probability that x is less than 3. So conditional probability is also something you can illustrate with a tree, in particular with a branch of a tree. Suppose we have a decision x equals x or x not equal to x, and we label those edges with the probabilities that they can occur. The lower one we're just going to have as a leaf. And the upper one we're going to lead to a decision y equals y. And the probability of that edge is the probability of y given that x has already occurred because it's a previous node. Now we can go on to get x of y equal little x little y. Notice these edges are independent, and therefore the probability of that edge is the probability of the first times the probability of the second. In other words, we've shown conditional probability. Let's look at an example. Suppose Jane uniformly randomly samples from 0, 1, 2, and she's picked a card, and I guess what Jane's card is, which means I uniformly randomly sample 0, 1, 2. John chooses from 0, 1, 2 a card that is not equal to either mine or Jane's, and then he tells me his card. Then I switch to the value in 0, 1, 2 that is neither equal to John's nor equal to my original guess. X is Jane's card, G is my guess, Y is John's card, and S is the value after I switch. Let's illustrate with a tree. Of course, this is the famous Monty Hall problem where I am the contestant and John is Monty. So we have got 3 doors. Jane randomly puts a car behind one of the 3 doors with goats behind the other 2. So in this example, x equals 1 for Jane. I pick a door, in this case the 0th door, and then John opens a door with a goat behind it. So in this case, his choice was y equals 2. Will switching my choice increase my probability of winning? The answer is yes, because John has shared information with me and I need to act on it. Again, we're going to illustrate with a probability tree. Begin with Jane making a uniformly random selection choice from the set 0, 1, 2. Each of those has a third. Then my guess of 0, 1, 2, each of those has a probability of a third. And for each of these nodes, I make a guess of what Jane picked. And so the probability that x is 0 and I guessed correctly is a ninth. The probability x is equal to 1 and I guessed correctly is a ninth. Probability x equals 2 and I guessed correctly is a ninth. Add those together, you get a third. I have a probability of 1 in 3 of guessing Jane's card if John does not share information with me. Let's keep going. Does switching to S have a higher probability of matching X than sticking with the original guess G? Well, let's put John in here now. So if Jane guessed 0 and I guessed 0, then John can either choose a 1 or a 2 with probability of half. If I then switch, then I would pick a 2 if John picked a 1, and that would have a 1/18th chance of occurring, just the product of those three edges. If John picks a 2, I'd pick a 1, there's a 1/18th chance. If Jane picks 0 and John shows me 2 and I guessed 1, then I would have to switch to 0. And we can see this process carried out through the entire tree. Then we can ask, what is the probability that switching matched X? So that's these blue edges here. And notice that if Jane guesses 0 and I switch to 0, then that's what we're looking for. And you can see those marked where they occur. There's a ninth for 0 and I guess 0, 2 different ways. A ninth for Jane picks 1 and I guess 0 but then switch to 1, and so on and so forth. There's 6 of those ninths, and 6 ninths is 2/3. So the Monty Hall problem, behind one of the doors numbered 0, 1, 2 is a car, behind the other 2 are goats. You pick a door, Monty opens a door with a goat behind it should you switch to the other door. So we just played this game with a probability tree. X is Jane, door with car behind it. G is my guess, I picked a door. Y is John, he opens a door that does not reveal the car, and then S, I switch. The probability of winning on my first guess is 1/3, but the probability of winning if I always switch is 2/3. The probability increased because I gained information from John, Monty's reveal. Switching uses the information that I gained, while the original guess G does not. That is, graph theoretic trees, decision trees, probability trees, etc. are intuitive and precise algorithms for representing and conveying information. For example, we use this in nearest neighbor algorithms. We did a split for KD trees, and a split again, and a split again, and a split again. And then to find a nearest neighbor, we did a series of decisions through a binary tree. There's many issues, this is just a general concept, but the key here is it's all based on being able to find our nearest neighbor by searching this tree. In fact, decision trees point to the broader role that networks play in data science and machine learning. Networks and graphs translate information, algorithms, decisions, etc. into actionable structures. Let's look at another application, imputing missing values. So imputation is the replacement of missing values with values produced through some predictive procedure. So imputing missing values changes the data, sometimes radically. So proceed with caution. And avoid imputation if possible. But if you do need to impute, it's going to be supervised learning, very often supervised learning in the form of regressor. Let me mention the types of missing values. There's modified completely at random, no pattern in why they're missing. Modified at random, data is missing because there was noise in the measurement process. Or modified not at random. Some process with probability 0 with respect to the model has modified the data. Regardless of which of the three it is, the process of imputation is modified not at random. So for example, grades data. 198 students in 8 classes, 141 passed, 57 failed, and there are many missing values, or NA not available. Maybe they didn't take the exam, or the instructor did not report the grade, or they took the exam in some alternate setting and it didn't get fed back into the data set. Notice, however, that none of these reasons for having a missing grade is the same as the process by which grades were generated. Missing values are almost never due to the process that produced the data originally. So imputing means there's a different process that's going to change the data than the one that produced the data. So if you have missing values, then you can drop the observations for which the values are missing, predict values to replace the missing values, or design algorithms that can use data with missing values. But it's imputation. If you decide to predict, then your training set should be observations with no missing values, validation set similarly, but the test set is the observations with the missing values. So we'll use a supervised learning algorithm to do this, to replace these NAs. It'll be based on k-nearest neighbors and graphs. In particular, it's going to be a process of imputation, which is not the same process that produced the data, but it will be via decisions and information in the data. We'll explore in the notebook. So for example, the Titanic challenge, predicting if a given passenger survived the sinking of the Titanic on April 5, 1912. This is a very popular, ongoing introductory competition at a place called Kaggle that they use to recruit participants to machine learning challenges and also to give them an initial background in what machine learning is all about. Now, Kaggle knows if a passenger survived and thus can evaluate those who participate. They don't tell you who did and didn't survive. You predict it, but then they can tell you how well you did. And you start with passenger data that they provide. So this is from the Titanic challenge. 12 features for 1,309 passengers on the Titanic. The training data is 891 passengers known to have either survived the tragedy or not. Test data is the remaining 418 passengers whose survival status is not given. Your challenge in this competition is to predict which of the 418 survived based on the training data. So let's look at pandas and the Titanic data. Notice we have an age feature for our Titanic data and some of the values are missing. So if we look at information on this data frame, you can see here are features, and this is a description of our features. If we look at a description of the data, you'll notice there are only 1,046 ages out of 1,309 possible. We've got a bunch of missing ages. So let's look at some of these passengers and notice that their ages are missing. And how are we going to impute those missing ages? Well, let's do a query in which we can, first we're going to put negative ones in the missing values so we can query to find missing values. We're going to use 15% for validation and the remaining 85% for training. So again, the missing values we put in as negatives. You can see the -1. So there's our validation data. What if we just use the average, 29.6 years, about 30? Well, that means every missing value is predicted to be an age of 29.7 years. And if we look at the differences and a histogram of that, look at the spread from -30 all the way up to 40. In other words, we're missing the actual ages by a bunch, and the median doesn't do much better. So if we look at the spread by replacing all the missing values by the median, once again we get a huge spread of -30 years to 40 years. But what if we base it on class and gender? So this could be slow, but what we're doing is using a decision approach to get a k nearest neighbors. And now we're going to impute missing values by looking at their gender in their cabin, and you can see we get better matches in some sense. So the histogram is not nearly as spread out. It's a little better, a little more centered around 0. And you can see that with this mean and standard deviation. So perhaps a better method for imputing missing values, and perhaps not. We need to keep testing and working on it. So why decision trees? Well, decision trees are useful and intuitive. Everyone can understand a decision tree. You can build diagnostics with decision trees. You can build algorithms using decision trees. And decision trees are trees. Graph theory and networks are important tools for representing the information in a data set, and in fact are the basis for much of machine learning.